Resuming recording in progress. There we go. Check one, check two. Hello, good evening, good afternoon, wherever you're watching in the world. Thanks so much for joining, Kieran Hinson, and wherever you're watching asynchronously. This is our week 5 IBM Data Science live session. Crazy week this week, so I want to make sure that I kind of allocate time on the correct priorities that I would focus on for y'all. So again, really, really big week. I have nothing in my slides, so let's just kind of go into some of the learning objectives here. This is our exploratory data analysis week, so there's a few things that I want to really drive home. Now that we've kind of spent the last few weeks doing data extraction, going out to APIs, going out to web scraping, doing extract, transform, load pipelines or your ETL pipelines, cleaning that extracted data up and then loading it into databases. And then last week we did our database week where we talked about database design, database history, and then practice writing queries to extract data out of databases back into Pandas. Now we're going to go into the real data sciencey like analytics. This is really where data science really starts kicking into high gear. Now that we have our data that should be mostly clean, maybe it's coming from a single source of truth, such as a relational database system. We want to start analyzing that data, looking for patterns, and then start building out a framework for repeatable predictive analytics. So you're going to see a lot of references to predictive modeling in this unit. And while that's important, no, it's going to be a framework for what we're going to dive into in week 7 and 8 when we talk about machine learning. So let's go over the official learning objectives, then I'll give you my learning objectives. So we got explain simple versus multiple linear regression, implement those basic regression models using Python, look at visualizations to interpret the goodness of fit of your models, as well as the difference between polynomial, multiple, and simple regression models. We're going to compare models using metrics such as R squared and a mean squared error. And then we're going to select appropriate evaluation techniques and regularization techniques to try to improve our modeling. Know that everything in these learning objectives is geared towards modeling. Modeling is only half of the week, right? So I'm going to spend the first half of lecture here talking about what's important to me, which is going to be around data wrangling, data cleaning, and data exploration. So the first half of the week is that exploratory data analysis. How do we read data in from our source? How do we clean it up? How do we make a numeric, fix our data types? And then how do we start exploring correlations, grouping aggregates, feature engineering, creating bins, all that good stuff, and then looking for patterns in our data that can then imply the benefit of why we want to do statistical modeling on top of our data. If there's no correlation, if there's no signal in any of your data set, then trying to build a model to predict and understand those patterns is kind of irrelevant, right? Finally, we're going to be reviewing all of this again, especially the machine learning, the predictive analytics learning outcomes. We're going to be reviewing all this again in week 7 and 8. So week 6 is our deep dive into visualization and dashboarding, interactive dashboard design. And then week 7 and week 8 are all devoted to machine learning. And honestly, what we're doing this week in terms of the predictive modeling half of the class is all just a foundation and setting you up for success for week 7 and 8. Because again, it doesn't matter if we're building a simple regression model, a polynomial regression model, or a random forest neural network. It's the exact same paradigm. How do we get our data ready for modeling? How do we construct multiple models? How do we evaluate those models using visualizations and metrics? And then how do we optimize and tune our models to generate the best performance? In week 7 and 8, we'll also touch on deploying and the productionalization, the ML ops side of machine learning and predictive analytics as well. All right, so I have my big ideas. Again, this is all my lecture notes. Everything's already backed up in GitHub for kind of the lecture today. So my big ideas, again, you'll see a lot of this is going to harp on kind of why data analytics matters and specifically data wrangling and EDA. So this is some of my big takeaways from the week. How do we clean our data to understand what variables influence our targets? How do we identify patterns? And is it even possible to build a model to predict future outcomes, right? Like we can't even do all the modeling work until we prove that there is adequate signal in the data. So we're going to be looking at a few different problems today. Can we find patterns to predict car prices? Can we predict house prices? Can we forecast sales or demand with seasonality? And then here's the full pipeline: data to insights to modeling to decision making. Let's see. So we're gonna go over a few things today. How do we use custom D or custom functions within Pandas, including kind of creating leaderboards, head, tail, info, describe. How do we do group buys, right? How to do all that good stuff. Understanding the data is always the first step of our analytics. We're then going to talk about pre-processing. How do we take our data, even if it is clean from a database? Just because the data is clean for a database doesn't mean that it's clean for predictive modeling. So how do we take that data and make it ready for analytics, data science, statistics? So we need to handle missing values. We'll touch on that today. We're going to format our columns and our units. We're going to normalize in terms of scaling our data, maybe doing z-scores for our standardization. We'll touch on that today. Creating new columns, feature engineering. How do we create new categories from numeric features? That is called binning, and vice versa. How do we create numeric features from categorical inputs? That's going to be called one-hot encoding or label encoding. You may hear that as well. And finally, with exploratory data and data analysis, we want to be able to generate descriptive statistics, visualizations, understanding the shape of data based on our box plots, scatter plots, violin plots, and then doing basic leaderboard aggregations, group by analyses, correlations to our targets. And it's only then that we dive into model development. So you'll see in my big ideas for my lecture notes, I had 6 sections. The first 3 are all EDA based, and the second 3 are all model machine learning foundations. So again, don't feel like you need to memorize everything around model development and the creating predictive modeling workflows. We will touch on it again in a couple of weeks here. So yeah, we'll come back to the machine learning bit here in a minute. Cool. Let's dive into some of the media sets. Good job on the forums last week. We got some participation in the week 4 forums, so nice work. The week 5 forums, there's a lot of potential topics to touch on here. Some of the more interesting ones to me as I was going through them over the weekend. Um, I think the model development one is pretty interesting. So I'm like, again, just setting your framework for week 7 and week 8. What does it mean to be selecting good columns, good features? Tell me the difference between all these different model algorithms. And besides these couple of metrics, what other metrics have you heard of? I think all of this is really interesting. So yeah, I had a couple of my favorites here. MAE, RMSE, residual plots, all of that's really good. So I think that's a really interesting topic. And then on the EDA side, um, mostly it's going to be like they're all pretty basic stuff. The data wrangling is pretty good. Like when would you need to clean your data? Like I think tying it back to real world use cases is really good. And again, we'll see that here today with the media sets. That when we're trying to predict like a housing price, for example, or a laptop price, that we're going to have different ranges and distributions within our feature set, which is why we need to do imputation, normalization, all of that good stuff. And just to prove that it's like a real thing, uh, let's see if I can find it in a pipeline step. You'll see that like in a common scikit-learn or in a common machine learning pipeline. I wanted to just get a picture of that. I guess maybe we'll see if there's anything here. It's all going to be kind of the same things, right? How do we fill in missing values, do our imputations? How do we normalize our data? How do we do That's a bad blog. But basically, how to do all this as part of a Oh, there we go. Pipeline for pre-processing. I wanted to see my beautiful scikit-learn pipeline. Maybe we'll get it going here. Yeah, then so yeah, we have all these different data transformations that we can fit in terms of our data pipeline to optimize for data leakage. As soon as I can find the pipeline here. Blah blah blah. Yeah, there we go. So we're gonna be doing, I want to see the full pipeline. Here we go. Yeah, that's not bad. So as we kind of have our pipeline here, you'll see that as we get our data ready from our database to really push down into our machine learning algorithm, that data needs to go through our null value imputation, our one hot encoder, right? And maybe just a pass through for any other remainder columns. So pretty interesting stuff here. And you'll see that this is not just for or we have function transformers, pretty cool. Not just for analytics and exploratory data analysis, but this pre-processing step is also important for machine learning and reproducible algorithm like training sets. All right, let's dive deep into a few of the media sets here. I'm going to start with 5.3. So 5.1 starts with just understanding the data. Basically, how do we check to make sure we understand what our data looks like? How do we look at the first few rows, the columns, the data types, etc. I'm actually going to start in 5.3. 5.3, I think, is a really interesting media set as it goes deep into pre-processing. So again, hopefully you've already watched some of these videos, but why do we need to deal with missing values? Why do we need to standardize our data formats? Why do we need to normalize, bin, and create our columns here? So yeah, long story short, it's really hard to find patterns in text or string-based data sets. So converting them to numbers allows equations and aggregations and patterns and signal to be a lot more visible to our downstream algorithms. So hopefully you already watched all these videos and we'll jump through into our first kind of notebook here. I think it's gonna be the second one. Yeah, the laptop data set. Should we do the automobiles? I was gonna do the laptops. I didn't want to do laptops. Yeah, we'll do laptops. All right, so let's start with the second example here. So this is going to be 5.3, should be 5.3.2, this one. And I'm really going to do two notebooks today. We're going to do this one, and then we're going to do the keynote activity, which is building kind of our models and things like that. All right, so in this lab, our goal is to take a real world data set on laptops and see if we can clean it up, do some basic analytics on it, and see if it will be possible to do any predictive modeling downstream. And I do have a hard out at 1:30 today, so same idea as normal. We're gonna try and fly through these couple of notebooks, do the quiz, and then get you out of here right at 1:25 or so. All right, goals for the lab. Deal with null values, fix our data types, standardize and normalize everything, visualize data, and fix our categorical data sets. So let's dive into things here. First, we're just going to be loading in our libraries, and then we're going to be fetching in our data sets. There it goes. Sweet. So we'll grab our data sets and we'll download it, and we should have this new laptop CSV. We can actually take a look at what this data set looks like. So already just looking at it, there's some really interesting things that are jumping out to me. This first column is doesn't have a column name, and it seems to just be an index or maybe computer ID or something. Then we have a few columns: manufacturer, category, screen, how many GPUs, operating system, cores. We got a good flow of numeric data fields, but we also have a couple of strings here in terms of the manufacturer and the screen type. So we'll say we have some data cleaning that we're going to have to do. So let's load in our data, our CSV. We're going to read our CSV into a data frame. And then from there, we should be able to take a look at it. So I'm going to run df.head to take a look at it, and you'll see, yep, there's our missing column name here at the start. And then if I run df.info, we'll see a few things here. So this is one of the most important functions you'll ever run when interacting with data sets. It gives you all of the metadata associated with a data frame. So there's a few things to point out. First, we have 13 columns and 238 rows. Note if you run df.shape, that'll also give you the row and column count. Next, we also have the data types for all of my columns. So we'll see that anything that's an object is a string. So as we saw when we looked at the CSV, manufacturer and the screen are going to be strings. Everything else is a number, an integer, or a float. We can also detect null values here. Anything that doesn't have 238 not null contains missing values. So we see that we have missing values in screen size as well as in laptop weight. So the three things that I always look at when doing a .info, do we have any missing values? Do we have to fix any data types? And do we have to fix any column names? So again, looking at my data here, we have null values in two of our columns. The data types look fine, but we have a bad column that's missing a column name. And if you were me, I prefer my column names to be all lowercase. Uh, cool. So first thing we're going to do is we're going to round screen size to 2 decimal places. So sure, whatever. I'm using NumPy for this, but you could probably also just use like the built-in .round function, which I think is a thing. Oh, that is a thing. Look at that. Cool. So you could have just done this as well. But whoops, where did that go? Drag and drop. Undo. Oh well. Whatever. So there's different multiple ways to do this. And I use NumPy, but whatever. Doesn't matter which way you actually do it. All right, next up, let's look for missing data. So we've already identified missing data, but here's a loop to do the same thing. Basically, it's going to look at the whether or not it is null. There's a built-in function in Pandas to detect that. So again, that's the other part of this exercise is just get more familiar with Pandas built-in functions, also like value counts, for example. So we'll see here that we have 4 missing columns in screen size and 5 missing rows in weight. So the first thing we're going to do is imputation. When you have missing data, you have a couple of options. The first is just to drop the row. So that's a pretty easy solution. If it has null values, then just drop the entire row. The second one is to fill it in. So when we fill in the value, we can either fill it in with the mean or median. And for categorical data, we can fill it in with the mode or the most frequent. So let's see kind of what we're going to be doing here as we start filling in, imputing with the mean. So I did my basic analysis here, which is these are the 5 rows that are missing weights. Basically, I just located where the weight kilogram is null. So we have these 5 rows that are null. These all look like real rows. So dropping them, I'm definitely going to lose signal in some of these other columns. And if we check the distribution, again, if we don't necessarily want to, if you probably learned this in the videos, but if we have a data set, again, a normal data set looks like a little bell curve. If we have a bell curve, the average and the median line up basically to be exactly the same. However, if our data set is skewed, so let's say our data set looks like this with a long right tail, then our mean and median are going to be different. Our median will still be about here, but our average is going to be pulled towards the skew, right? So our mean here is to the right of the median. So when we think about imputing our rows, if there's skew in the underlying data column, then imputing it with an average could introduce more bias and variance into the column than is needed because not all those rows are going to have that high average expectation, right? So typically it's best to look for skew in your column before imputing. So that's what I'm doing here. And I notice that the average and the median are essentially the same. That implies that the shape of data of the data distribution is approximately normal, which means it doesn't matter if we use the average or the median. Further, I also wanted just to highlight that we only are missing 5 rows out of 238, which is only 2% of all rows. So because we're only missing 2%, it doesn't really matter if you drop them. So dropping is finally fine in this case because we're not missing that many rows, but the exercise told us to impute them. So fine, we will impute them. And essentially, here's the code on how to do that. We just grab the average of the weight column. This as type float is not needed because it's already a float, but it is there anyway. So whatever, blame the messenger. Don't blame the messenger. But when we do that, we can then replace the null values with that average rate, average weight. So let's do that. And now when we check, we are not missing any more rows. And just to confirm, our imputed weight here does have that 1.86. So that should be the same value that we identified up here. So we were able to impute the values successfully. Hooray. Next, we're going to look at screen size. Screen size is really interesting. So screen size, remembered we were missing 4 values. And screen size, while it's a number, we're actually going to see that it's not really a number. We'll talk about that in a sec. So one thing I want to do, we're doing that first skew analysis here. The average is 37.2. The median is 38. So we have the opposite of what I demonstrated earlier. Because our average is less than the median, that implies left skew. So our data set looks a little bit like this. So we got a little bit more skew over here to the left. This implies that we have some small screens, maybe an iPhone or an iPad or something, that's biasing this data set, but that has a smaller screen size than expected. So there's a little bit of skew here, not a ton, but more impactfully, if I do the value counts, notice that a majority of my laptops all have the same screen size. This is not a continuous numeric feature. This is a categorical numeric feature that we have specific screen sizes that our laptop may fall into. So we have 89 laptops with a screen size of 39.62, 64 with a screen size of 35.56, etc. So because of this, imputing with the mean or the median, I'm looking at both of these numbers, 38.1 and 37.26. None of those are actually options here. You can't actually buy a laptop with a 37.26 screen size. So instead, we want to use the mode, the most common value. So your mean, median, mode, and range. So to get the mode, we're going to call IDX max, which will get the max of the value count. So that should pull back this value right there. And then we're going to replace missing values with this 3962. And then, as we kind of mentioned earlier, we do have some smaller screen sizes here. We have 8 laptops that are all under 32 inches, which is a little small for a laptop. All right, so hopefully this worked. And then if I do my .info, we no longer have any missing values. Hooray. All right, so that was all null values imputation work. Now let's go into more data wrangling, specifically with our data types. Um, uh, Originally, I read it in fine. These are already floats, but if we wanted to convert them to float or to floats, we can do it like this. We're selecting these columns and converting them to the type float. And then I'm also going to be updating the column name. I'm going to be changing this from unnamed 0 to ID. And I probably should do that in place, but that's probably fine. Actually, I'm going to do it in place equals true. Cool. So there we go. We've renamed the first column to just be computer ID. All right. Next up, let's work on our data standardizations. So one thing to note here is that our units are all over the place. Or not really. I think we're all in the metric system. We have kilograms and we have centimeters and then we have dollars, I think are our units here. So what I want to do is because we're going to pretend that we want to run these in imperial units, we're going to convert from centimeters and kilograms to inches and pounds. This is essentially um, feature engineering. We're creating new columns from existing columns. So we're going to create new columns for weights, pounds, and screen size inch. And when we do that, it looks like this. So now we can see that my laptops are 14 inches, 15 inches, whatever. And the weight in pounds is up to like 5 pounds or something. Next up, we want to look at when and why we may need to do data normalization. So typically, this is we're going to start thinking about range, right? We've talked about mean, median, mode. Let's talk about range and how that impacts our data here. So when we are predicting a column, so in this case, we want to try and find signal to predict price. That's our ultimate goal here. And as we start looking at that, when we start training models, computers are dumb, models are dumb, algorithms are dumb. At the end of the day, as smart as AI and all these things are, especially the algorithms we're going to be using, and especially this week, they're all pretty dumb. Linear regression, very basic, been around for a few hundred years at this point. People were doing them with pens and paper back under an apple tree. So anyway, with regression models in particular, if your columns have different ranges, for example, like this one maybe goes from like 1 to 10, this one goes like 1 to 3, but the storage gigabytes or CPU frequency, like if they have different ranges, this one goes from 0 to like 3 as a range, right? Then your algorithms get confused by that. They think that having a big number could imply more significance. So their models are dumb. So let's actually take a look at this in action. If I do my df.describe here, I get my mean, median, and range with my min and my max for all of my numeric variables. So what I'm going to look at here, let's look at the range, right? And I'm going to ignore ID because ID doesn't really matter. But as we start looking across our numeric features, we have 1 to 5, 1 to 3, 1 to 2, 3 to 7, 12 to 17, 1 to 3, 4 to 16. Those are all fairly close, right? They're all pretty close to each other. But if I look at the storage gigabytes, we go from 128 to 256, which makes sense because it's looking at like bits and gigabytes and gigabits and stuff. But that range is a lot higher than 3 to 7, right? So because of that, it could be I wouldn't be surprised if the model would see undue significance in those larger values. The other one worth just pointing out, CPU frequency going from 1.2 to 2.9. That's a pretty tight range. We could probably try and expand that out a little bit more if we wanted to as well. So this is where we're going to be using one of my favorite libraries, which is Seaborn. Seaborn allows us to create density distribution plots or histogram plots. That's kind of what we're going to be looking at here. We're creating a histogram plot of price, and this draws the shape of data much better than I can. So again, notice looking at price, this is a right skewed data set. Most of my data is about $1,500, but we have a couple laptops that are almost $4,000. So we have a little bit of right skew in our target. We can do similar analyses for our features. So let's look at CPU frequency, and we'll see CPU frequency is kind of bimodal, kind of all over the place. We kind of want to clean this up, standardize it down. So we are going to scale using min-max frequency here. So essentially what we're doing is that we're dividing each value by the maximum of the CPU frequency. This is called a min-max scaling. And when we do that, you'll see that it's the same shape, but our range is now forcing the range to be between 0 and 1. This is also what a standard scalar can do. Scalars can do z-scores. So in this case, we're going to be scaling using z-score standardization, basically standard deviations. We want to make sure that we standardize everything within a few standard deviations of the mean. So that's what we're going to do here. We're going to create a new column called price scale that is scaled using a z-score. And when we look at the distribution plot of this, hopefully it's nothing too crazy. There it goes. It looks a little bit like this. So you'll see that we're centered now around 0 standard deviations, but we do go out to plus or minus 5 standard deviations on either side. And this little bump here at 4, that's going to be our $4,000 laptops. And then if I look at my df.describe for my normalized columns, you're going to see that my normalized columns are going to be much more within that 0 to 1, -5 to 5 range. Big idea here with standardization and scaling. By scaling your numeric features so they're all within the same scale, whether it's 0 to 1 or -5 to 5, it allows particularly less advanced regression type models to not overstate importance simply based on the value size, right? All right, let's keep grinding here. Let's move into our last couple tasks. This is going to be more feature engineering work. The first is how do I take a numeric value and turn it into a category? So a common use case for this is like age ranges. We all have a numeric age that's continuous, 0 to 120 or whatever. But we commonly see these binned as ranges. Am I under 18 or under 21? Am I 21 to 30, 30 to 40, 40 to 50, 50 to 60? What is your age range? Common idea, same idea here. How do we take my numeric feature of price and bin it into low, medium, and high values? So because of this, we end up with using a new pandas function called pdcut. Great function. You should look it up. And again, that's the other big idea that I want to get across in this notebook is get familiar with pandas, get familiar with Seaborn. Don't just focus on the modeling piece. So let's run this. We end up with our bins here, and then we can plot this as well. And wow, we have a category, right? This is, we have 160 cheaper laptops, 80 medium, and less than 20 expensive laptops. So pretty cool. Finally, let's go the other way. How do we turn from a category into a number? At the end of the day, we want to be creating averages, looking at variance, standard deviation, running equations. You can't really plug a string like low or IPS panel or whatever into an equation. Instead, you have to plug in a number, right? So with indicator variables or one hot encoded variables, we end up with zeros and ones, binary representations of the string that we can then use in our equations. So I'll show you a quick example of this. Notice that we have a whole bunch of manufacturers here, right? I'm actually going to use manufacturer for the one hot encoding tonight. So let's say we have Dell, Lenovo, HP, Acer. Again, you can't really plug Dell as a string into an equation, but we can get dummies on it. And what this means is that we end up blowing out this feature. Instead of having one column of strings, we end up with a dozen columns with indicators 0 and 1s. You'll see these binary features. 1, 1, 1. What this indicates is that the manufacturer in row 233 is a Lenovo. The manufacturer in row 1 or row 0 is an Acer, right? So that's why it's called an indicator variable. And a lot of weird names for this because Pandas also calls this like a dummy variable. But in real life, it's called one hot encoding. So you should definitely have that in the back of your mind. And again, don't worry, we're going to come back to this in week 7 and 8, like pretty intense. So don't, this is all just familiarity, getting yourself know what you don't know, right? And I really want you to get in your head pandas and data wrangling, EDA, data distributions, and Seaborn this week. All right. Cool. So let's see. We're gonna do the same thing for screen here. We're gonna get our dummy variables, and then we're going to connect it back to our original data frame. So when we do that, we end up with this bad boy right here, where screen has been concatenated onto the end with a 0 or 1, depending on its category. We can do the same thing for manufacturer. I'll just do that down here. Um, and I'm not going to bother renaming any of the columns for that. So it should end up looking something like this. Whoops. Boom. And so notice that now we've added our manufacturer columns as columns here on the right. And if I look at my df.describe or df.info, this is exactly what we want to see. We have 0 missing data. All of our column names are valid, and all of our data types are valid numbers, right? We don't have any string data left in there. Beautiful. All right, big ideas from here. What I really want you to get across, exploratory data analysis. How do we start exploring our data? How do we look for patterns, right? How do we start cleaning and wrangling our data well enough that we can make visualizations, look at distributions, look for skew, keep in mind the mean, median, mode, and range, right? What does that tell you about the underlying data distribution? How can that introduce noise or signal to a productive model, right? Lots of good use cases for that. Let's see. I think we're doing pretty good on time here. Been about half an hour. So let's take the next half an hour and go over the capstone project. I'm actually going to download this notebook and boom. Cool. All right, so let's jump over to the next, to some of the other media sets here that are worth talking about. I won't have time to do all the notebooks that I want to do this week. I really liked 5.5. I may just show you quickly one that I did in 5.5. Mostly what's important here is, yeah, like what is EDA? Why is it important? How do you look at these different distribution plots? How do you start running correlation analyses? So yeah, I'll actually just show you one that I ran earlier, just because we don't have time to run everything. I'm gonna do the laptop data set again. And then you can always check out my notebooks in GitHub if you need help as you run through these on your own time. And I run all these locally, which is why my code's a little bit different. But you're gonna see here that now that we have our clean data, that's already like looking really good. We can start making different types of visualizations, like a correlation scatter plot. Is there a relationship between CPU and price? And it looks like there is a weak correlation, some weak signal here, right? Same thing between price and screen size, price and weight. We're doing correlation analysis. We're looking for signal in our data set and our patterns. Similar thing with box plots. Again, I'm using Seaborn here. Learn to love Seaborn. It's awesome. And we can see that there's some patterns here. Category 5 laptops seem to always be more expensive. So that's some signal that we're finding in our group by. This is a grouping analysis, a group by, and we're grouping by category and looking at our analytics there. Same thing for GPU. GPU 3, or I think that's a laptop having 3 GPUs. Those seem to be on average a little bit more expensive. So we're going to group by analytics. And then, yeah, here we are. We're doing our pivot tables, leaderboards, correlation plots, and then looking at some correlation analysis. You just basically looking at our R value. Yeah, I want to see if there's any signal in our feature set versus our target of price. Cool. So definitely recommend running through that on your own time. And then we get into the fun stuff, which is building out models. And again, in week 5, we're going to take this as a very high level introduction to modeling and to machine learning workflows. We're going to go a deeper dive into this in a couple of weeks, as I've already said a million times. So don't feel like you need to memorize or understand everything on it here. So mostly what we want to go over today is the difference between the various type of regressions that you're going to be doing. So a regression, we'll start here. A regression model is a algorithm, and in this case, an equation specifically, a mathematical equation, a line of best fit, if you will, that predicts a continuous numeric target. So we're only looking at numeric targets. We're not doing classification. We're not trying to predict probabilities. We're trying to predict numeric values here. So in this case, you want to predict the price of a car given its miles per gallon. We end up with a line of best fit, y equals mx plus b. So in this case, b is a constant, m is a constant or a coefficient. X is going to be your miles per gallon. So something times 55 plus something equals 5,000, right? That's kind of the goal here. And our goal is to be able to fit this equation based off of all of our observations in our data set. So that's the first thing to know is that when we do specifically a regression analysis, we're predicting a target, a continuous numeric target. And when we're doing linear modeling, that's what this is, linear regression. We're doing linear modeling. Even polynomial regression is still linear modeling. When we do linear modeling, the algorithm is going to be rooted on a mathematical equation that's also founded in mathematical proofs. So we'll see if we end up with a good, yeah, there we go. So here's our y equals mx plus b here. In their case, they did y equals b naught plus b1x. That's the more mathy way of writing out this equation. So good to look at there. Note that one way to interpret how good your equation is by looking at the errors. Residual is a fancy name for error. Basically, it says based on your equation, how far off of reality were you actually, given this data set? You predicted the price to be 5,000, but it was actually 4,500. Your residual is $500. You were off by a margin of $500. I want to breeze into the more advanced regressions. So you may see some other type of algorithms used in this class. First one, they're doing polynomial here. Well, let's stick with polynomial. While a normal equation, as I already showed you, y equals mx plus b, one way to make this equation more complicated and therefore more robust and more capturing non-linear or more variance in your data is to add exponents. So your exponents would be your squares, your cubes, right? Your to the fifth power or whatever, right? That's what a polynomial regression does. It starts fitting equations such as y equals mx cubed plus mx squared plus mx plus a constant, right? So it starts fitting a lot more coefficients to much more polynomial terms. We still only have one column here, right? The only feature that's being used is still x. Notice that, right? We only have x used here. This is still a simple linear regression in the fact that it's only using one column to predict one target. But by adding in polynomial elements, we're able to get more out of that one column, right? And instead of just doing y equals one column plus a constant, we're able to now look at the relationship of its cube, of its square, right? Which can usually and sometimes which is usually able to capture more variance. But sometimes it can also overfit your model. Your model is getting too reliant on the training data that it doesn't capture real world signal. So that's something to watch out for. And then the third one that you should know needs to be multilinear or multi. I guess they didn't actually have it on here, but you'll also hear like multi-regression, which goes from using one column to using many columns. So instead of just using miles per gallon to predict price, let's use miles per gallon, and horsepower and weight and year of make. things like that. How do we use more columns? That again, those columns could have polynomial terms. They could not, right? But at the end of the day, we're going to be creating an equation. So let me actually pull that up. So when you do a multi-regression analysis, you'll see that we're going to end up with multiple x's here. We have x1 plus x2, right? And that goes for all eternity, depending on how many columns you want to use. And then if we introduce polynomials, this also gets even more complex because, yeah, you end up with something that looks like this, where you can have your x1 plus your x squared x1 plus your x2 plus your x squared x2 all the way through to the end. So you definitely need to know about all three of these. Your simple linear regression versus your multiple linear regression versus your polynomial regression. And I'm actually going to steal that image and I'm going to slap it in our live video, our live Q&A chat. And again, Hinton, if you have questions, definitely feel free to drop them in chat. Karen is looking pretty bored, so put them to work. Or Karen, if you have any additional content or context that you want to bring in
Or
here.
no, I was multitasking, writing a post on something
No, you're
additional.
all good. Yeah. So I wanted to drop this into the live
But
session.
yeah, but yeah, you can. If you have anything questions, please put in the chat. I'm watching for any chats because I know you don't want to make noise where you are.
So let me dive into the last notebook here that I want to do, which is going to be in 510. This is the keynote activity of the week is that we want to predict the price of a house from Seattle using data from May 2014 to May 2015. So the data is a little bit old, but it's still a pretty fun activity here. So let's open it up and it's going to do everything that we've already done. We're going to take this data set. We're going to do some data wrangling, some pre-processing, and then we're going to create a couple models and evaluate those models using regression metrics such as R squared and mean squared error. So a good notebook, and obviously it says 75 minutes. We're going to fly through it in half an hour or less. So definitely take the time to do this notebook on your own time. Oh yeah, one thing I put this in my forum post, but you do not need to take and save screenshots for this. Just as with any other week, the grade for Module 5 only comes from the Module 5 quiz at the end of the module. But I do always recommend backing up, saving your notebooks, and saving the content into your own GitHub repository to showcase your portfolio of work that you completed this bootcamp. All right, let's get down to business here. And let's start diving in. All right, so first thing we're going to do, we're going to load up all of our libraries. Going to be all of our favorite libraries, Pandas, NumPy, visualization such as Matplotlib and Seaborn, and then we're going to start loading some pre-processing work in with scikit-learn, specifically around our z-score standard scalar, and then we're going to be building models around linear regression and polynomial regression here. So it should be this is a very heavy notebook. It's a very heavy activity, but it should be a fun one. So we'll wait for all of our libraries to load. What's taking time here is that we're waiting to install Seaborn, but it shouldn't take too long. All right, let's get down to business. First thing we're going to do is we're going to download the housing data set, and then we're going to load it into a CSV. All right, and then we'll load it into our data frame and take a look. And here we go. There's a few things that's already jumping out at me. This date column looks kind of funky. But let's actually take a quick look at our data. I'm going to use df.info here. It's our favorite function in all of Pandas. And whoa, we got a real data set here. How exciting. I love me a real data set. So what's so exciting about this data set? It actually looks real. So we have 21,613 rows. and 22 columns, which is a lot of columns. All of our column names look pretty good. They're all lowercase. We have this weird column that we probably can drop. But let's look at our first three things: data types, null values, and column names. Data types, I'm super happy. Everything is a number. The only thing that's not a number is date. And as we saw, this should probably be a date time. It shouldn't be a string. But that's the only bad column in here. Everything else is already numeric. So we don't have that much encoding. That's why we didn't have to import a one-hot encoder or get dummies, because there's nothing to get dummies on. Unless what I'm thinking though is maybe we can parse out the month from the date and we can use the month as a category, and that can maybe have some signal to it as we put it into a model. Looking at null values, we definitely do have null values here. Bathrooms is missing 10 rows. Bedrooms is missing 13. That looks like it. That's like the only two columns with missing values, though. So my notes are that we have one bad data type, which is the date column. And if I were you, I would drop the null values. They're not worth imputing because there's not very many that are missing. So yeah, we have less than 1/10 of 1% is the missing data, right? 13 rows out of 21,000 is 0.06%. So really, you're gonna have no harm by dropping those rows. By calling dot describe, we can get the statistical summary, we can get the median, mean, and our range. So one thing to look at here is definitely we're going to do some scaling. I'm looking at my ranges. Bedrooms 1 to 33, that's also crazy. 33 bedrooms, that may be an issue. But square footage goes from 290 to 13,000 square feet. So that's a really, really large range. Same thing with square foot above ground and basement or year renovated. So definitely our square footage seems to be skewing our range. So maybe that's a good note to put in. Ranges are all over the place. Likely a standard scalar or a scalar will help. All right, so let's do some data cleaning here. All we're going to do is we're going to get rid of some of these unused columns, and then we're going to get rid of our null values. Oh no, we're doing imputation. How fun. So as we already determined, we have 13 null values for bedrooms and 10 for bath. What we're going to do here is imputation. These are going to be categories. A majority of my houses either have 3 or 4 bedrooms. Even though they're numeric, they're not continuous. I guess you can have a half. You can't have a half bedroom. You can have a half bath, but not a half bed. So we'll see that the average is 3.3, which you can't actually have as a number of bedrooms. So we're going to be using the mode, which should be 3 here. So we're going to be filling in those null values with the mode. That shouldn't say mean. I'm going to change that to mode. And so when we do that, that should have filled it in. Similar thing for bathrooms. I'm going to swap that out for mode as well here. And that should have fixed everything. And if you're curious for bathrooms, it should have been 2.5 bath is our mode. It's our most frequent number of bathrooms. All right, for dates, we can fix our date time by simply calling this function. We're going to take this date, we're going to cast it to the date time format, and here's how we're going to format it. And that should be able to parse it out correctly. And it did. We were able to parse it out as a date time. Hooray. And that's kind of what the date looks like. And then from the date, we can pull out the month as a new column as well. Like I mentioned, that can be a feature. October, December, February. Maybe that can help us. I think that's the month that the listing was put up. Maybe that'll help us understand price. Is it always more expensive in the summer or the winter to buy a house? All right, let's do some EDA. We already noticed some weird things. So remember a couple of weird things we already found was that there was like 33 bedrooms in a house. So that's part of EDA, right? Where's their outliers? Where is there weird noise in your data? So in our case here, we're going to look at the number of floors, see how that looks, and that looks pretty good. Most of our houses have between one or two floors, but one of them is three and a half. It's kind of strange. I'm not really sure what that. Maybe that's like an attic or a basement. It's that extra half of a floor. We can look at the distributions. So our goal here is we want to see whether a house with a waterfront view or not has a higher price. We can look at that with this Seaborn box plot function, but I'll give you a trick. My favorite Seaborn function is actually violin plot, which shows the same thing as a box plot, but I think shows the distribution of the shape of data a lot easier. So kind of what we're looking for here, the ones on the left are not waterfront properties, and the ones on the right are waterfront properties. So we can see I'm looking at the white lines here or the hump of the distribution, but we can definitely see that uh, waterfront properties do seem to be more expensive than not having waterfront property. So again, that's some signal here that we found in the data. Now we can start building some correlation plots. That's what we're going to do here. Is there a correlation between the square foot of the living space and the price? And wow, there is. Crazy. I would never have guessed that. Just kidding. I totally would have guessed this. There is a positive relationship. As the square footage of the house goes up, the price of the house also goes up. Just kidding. All right, we can look at the exact correlation of this, which should be 0 0.7. So this is showing all the correlations with price of all of my columns. So we see that we have a lot of strong correlations here. Square foot, the grade, more square footage, the number of bathrooms, as well as how good the view is. Columns that don't correlate, square footage of the lot versus the house. And then the month doesn't really correlate. Zip code doesn't really correlate either. But latitude does a little bit. So I feel like there is some location in Seattle that would impact the price of the house more than others. All right, so let's decide to build a model. For some reason, they want you to build a model using longitude. I'm already looking at my correlations. Longitude does not correlate with my target, which means that I would expect this model to be garbage. Good job. Yeah, it's going to be a bad model. So let's check. Let's build our linear regression. And yep, we got a bad model. So this score is going to be giving us the R squared value. For R squared, it's going to be R squared means the percent of the variance that the model explains. And it's going to be between 0 and 1. Higher to 1 is better. So this basically implies that there's no signal in this model at all whatsoever, which again is expected. Let's contrast that to the square foot living. Square foot living gives us an R squared of 0.49. So about 50% of the variance in the data can be explained by square foot of living. And if you're curious, R squared is this R value squared. So we'll prove that here. 702,035 squared is 0.4928. I love it when math works. All right, let's do a multi-regression model here. Notice we haven't done polynomial yet. We're just doing a multi-linear regression model. So remember, a multi-regression model uses multiple features. So in this case, I'm using all of these columns. Note that this does introduce multicollinearity. There is some relationship between the columns here. Square footage of the basement affects square footage of the living, which affects square foot of the above. Where like all the square foot columns are all the same essentially. So we probably should only be using one of those, but whatever, like total square footage. But it's fine. For our use case here, we just want to showcase what a multiple linear regression looks like. So notice that now my features X will be all of these columns. My target is still price, and we should now be able to fit a pretty strong model. And we're able to improve our R squared value from 0.49 to 0.657. So that's really exciting, right? By adding in more features, we're able to explain more of the variance in our target, which is good. Note that as you kind of had diminishing returns here due to the multicollinearity, as I'll showcase here. If I look at the correlations of my features, all the square footage columns correlate really well to each other, right? As well as the number of bathrooms and things. So one important aspect to learn with linear regression is to minimize multicollinearity, right? We want independence in our observations in our feature set, and we want our predictors to not really be correlated with each other. But again, you can ignore that for right now. That'll come back to bite us in week 7 and week 8, though. All right, last thing here, let's fit a full pipeline together. I want to scale my features using our z-score. I'm expecting that should help our model as well by reducing some of the noise based out of the ranges. We saw the disparate ranges in our feature set. So the scaler should help with that, especially for linear models. We're going to introduce polynomial features, which I think by default, let me grab the docs on that. I think by default, it's just going to be up to degree 2. So that means we're going to add square terms for all of our features. So not only are we going to have x1 plus x2, it'll be x1 plus x1 squared plus x2 plus x2 squared for every single one of my features. Notice that you can have that be up to cubes if you want, but we're just going to keep it with a degree equals 2 for right now. And then finally, we're going to then train our linear regression. So here we have everything put together into a beautiful pipeline. We're going to fit my multi-linear regression, my multi-polynomial linear regression with all of my columns against price, and then look at the R squared. Drum roll, moment of truth. And wow, with the exact same features, right? The exact same features, just by adding in a scalar and those polynomial features, we've increased our R squared again by a lot, all the way up to 0.75. So we've gone from 0.49 with a simple regression, 0.65 with a multi-regression, and 0.75 with a scalar and a polynomial regression. But we're not quite done yet. In fact, we can now start framing this on how a real machine learning workload would look like, which would be splitting our data into train test splits, which is typically done to allow us to interpret how our model will look in the real world against unseen data. In this case, we're holding out 3,200 rows, and we're only training on 18,000. And let's try a different algorithm. We're still going to be using a linear model. A ridge regression, you don't need to know the details of it now, but a ridge regression is still a linear regression. It's still a linear model. It's going to be defined by a mathematical equation rooted in mathematical proofs. So let's train a ridge regression. Basically, what a ridge regression does is that it tries to minimize multicollinearity. So if you do have columns that are related to each other, ridge will try and only emphasize the columns that matter, I guess. It's a band-aid for poor feature selection, but whatever. It's my own opinion. Next up, let's run. Notice that we improved a little bit here. We got pretty close to the linear regression model of 659. What we want to do now is add in our polynomial features. And I'm kind of mad they didn't do the scalar. But by adding in the polynomials into our ridge, you should see that we should have comparable performance to our polynomial before. And if we added in our scaling, this should also improve it even more here. I want to see if I can do it. I don't think so. Maybe. We'll see if this works. I'm going to see if I can add in Ridge into our pipeline here. So my model's going to be Ridge instead. There we go. And then I wanted to see if we can do a pipeline. There we go. Cool. And then we already have our train test split. So this should just be, we're gonna fit on X train, right? Yeah, fit on X train and Y train. We did here. Fit on X train and Y train, and then we're gonna generate our scores. So let's do that as well. This would be pipe.score X train, Y train, and then X test, Y test. Cool. So this should be our full pipeline here where we've scaled our data and then we can see how good it looks. Didn't like it. What didn't I like about it? Ridge is expecting 78 features as an input. That's crazy. Oh, duh. Boom. There we go. So here's my final result with the scaling added. You'll see that we did beat the one up here. So we've gone up to 754, which is pretty good. We're a whole point higher. And I don't know if that's any better than our last one. No, it is better. It's a little bit better. It's a little bit better than what we did originally. And it's more best practice because we have a train test split. Cool. Let's recap this notebook, big ideas, jump over to the quiz and call it a class. So big ideas from this final activity notebook, and again, just takeaways from the week. Your big ideas for this week is pandas for wrangling and an exploratory data analysis, and then ending with a foundation for model building. So I really want you to get practice with your pandas for data wrangling. So get comfortable with all these pandas functions, your head, tail, info, describe, PD cut, converting data types, value counts, dot replace, all of these really critical functions for being and interacting with data using the Pandas library. Next, the importance of exploratory data analysis. After we've already cleaned up all of our data, we need to start looking for weirdness. So we probably should have looked at that bedroom with 33 bedrooms. Probably would have dropped that row if I was being honest with you. Also looking for distributions, looking for skew, looking for outliers, and then most importantly, looking for signal. Where is there an impact or signal against our target? Where our target in this case is the price of the house. And then finally, after we've done our EDA, we've detected signal, we know what our patterns are, we know what we want to do. Let's introduce fitting some basic modeling. Specifically, we introduced linear modeling for regression problems. That's what we did today. Regression linear modeling. So we're predicting a continuous numeric variable using linear models, linear mathematical equations that have been rooted in proofs going back a few hundred years. These algorithms are easy for computers to do, fully explainable because they're rooted in math, and they're usually a good benchmark for determining predictive prowess of your data set. So in our case, we split our data into training and testing sets. We tried different algorithms, linear regression, ridge regression, and we also added in a full pipeline using a scaler to handle our difference in ranges, as well as adding in polynomial features to try and capture more nonlinear effects in the data set. And all of this worked out really well. We improved our baseline R squared from 0.5 all the way up to 0.75 with the same data set, just by tuning our features and enhancing our pre-processing just a little bit. So good work. We're going to go hard on predictive modeling in terms of evaluation in week 7 and 8. We're going to do regression versus classification. We'll be talking about more exotic linear models as well as your tree-based algorithms. And we'll talk a lot more about model interpretation, model evaluation those weeks as well. We'll end by talking about neural networks and ML ops for model deployment and model productionalization as well. So a lot to look forward to the next couple of weeks. Remember, week 6 is all about dashboard design, interactive design, making visualizations to tell data stories, business intelligence. It's a pretty fun week, culminating in an interactive dash data application with multiple interactive graphics that you can interact with as an end user, which is really cool. All right, plop any questions about this activity in the chat, and then I'm gonna hop on over into our quiz to end the day. Again, yeah, so we're going kind of breakneck today. I got a hard out here in about 10 minutes. So we'll see as we go. Um, I think Karen, you emailed me about something up with the quiz, so just call me out if I go over it. Maybe it wasn't week 5.
No, that was the practice quiz.
Oh, okay.
Yeah, no,
Uh,
the real quiz is fine. I mean, I got
cool.
100, so it must be fine.
All right, well, let me try my best here. Hopefully I remember some of these answers. All right, so I'm starting with the week 5 quiz here. This is the only thing that's due for a grade this week in week 5. Remember, when you do hit week 9, though, week 9, all the notebooks and media sets, they build for the capstone. So for week 9 and week 10, you do need to save those notebooks because they will be graded by Karen and I as part of your capstone submission. But weeks 1 through 8, the only thing you have to do is the quiz. So let's see how we do here. This is the week 5 quiz on exploratory data analysis. What does the following line of code do? It initializes a linear regression object, assigns a linear regression model. I'm saying it's not A because it hasn't fit the model yet. B obviously doesn't do a
It's
fit.
D.
C doesn't do any predictions. So I'm going with D.
D. It's D is right.
Yep. What's the maximum value of R squared? We went over this. It's the percent of variance explained. So 0 to 1. So 1 is going to be the maximum. Let's look at our pipeline here. What steps does the code perform? We initialize our pipeline. We start by scaling our pipeline, our features. We then pass those scaled features into a linear regression model. We define a pipeline based off of that input. We fit the model with our input training data, and then we get our predictions. So this performs a prediction using a linear regression model. Let's go through why it's not any of these other ones. It's not A, there's nothing about polynomial features here. It's not B, because again, it doesn't show correlations of anything here. And it's not C, that would be the score. Coefficient of determination is just R squared. So it's not calculating the R squared. It's not giving us a pipe dot score. So it's not C either. So it says D, generating predictions with a linear regression.
Wait a second. Look at that question now. It says a typo. I didn't even see
I
it
mean, pipe
before.
should be on a new line. Is there something
Yeah.
else?
Yeah, I
Because
mean,
D is all
we could in
lowercase.
Python put a semicolon there, but that's a very rare use.
Yeah.
Usually put a new line.
What is the order of a polynomial created with this one? This one's kind of silly. This is creating a polynomial with a maximum of 2, right? I think I missed this one last time. Basically, it's going to create polynomials of x and x squared. So it's got a maximum of 2. It's not just 2. It doesn't just create x squared. And it's not a minimum of 2. And it's not 0 and 2 inclusive because it doesn't do x to the 0. It just does a maximum of 2. Question 5. This is our y equals mx plus b. This is our linear equation. Variable y represents our target or dependent variable. What's the result of the following code? We're going to go into cross-validation in week 7, so don't feel like you need to know it super well this week. Essentially, what we're going to be doing here is that we're going to be doing generating the predicted values. We're getting the predictions of the data using cross-validation. I think that's all it's doing. We're not looking for A. There's no alphas here. There's no out of sample evaluations. And what's wrong with D is that usually when you fit a cross-validation model, it is taking the average R squared. But this says two folds, and we're doing three folds here. And also, this isn't doing the score. It would say cross-val score, similar to the above problem. This would say pipe.score if we were grabbing the metric. But we're not grabbing any metrics. There is no R squared here. We're getting predictions. So predictions versus metrics. So this is going to be B. We're generating the predictions of the data using cross-validation. A few more here. How would you organize the values 110 and 100 as alpha for a grid search? Your option's going to be A here. Basically, the parameter we want to tune is called alpha, and the values we want to tune are 110 and 100. So we're using key value pairs to organize the parameter and its values. B is wrong because it doesn't mention that we want to interact with alpha at all. C is wrong because these parameters are independent of the algorithm, so we don't care about ridge yet. And D is wrong because alpha is not a function, it's just the name of the parameter that we're tuning. Question 8. Consider performing the following steps. Train test split, create a linear model, find the average R squared, add in a whole bunch of polynomials. That's crazy. Retrain the model, and we've improved the model. Considering these steps, which the following is correct, you should use test data to test the model further. Sure. You should use a simpler model. Sure, because this is crazy. You should create another linear model with all the data, compare the results. That's wrong because we don't want to use all the data. We want to use our train test split. The 100 letter polynomial will work better. That's also wrong because 100 order degrees is crazy. So it's either going to be A or B. So let's actually take a quick look at this. We're looking at the value on the training data. So I think that's critical. Notice that it's looking at the performance of the training data. When we evaluate metrics, we want metrics to be evaluated on the test set. So I'm going to go A here. Even though using 100 order polynomial is crazy, it could be an edge case where it actually does work in this situation. So I wouldn't be, given what it's told me, I don't think just declaring to use a simpler model is the best answer. It's probably a good answer, but until we know the performance of the model on the test set, we don't want to claim to use a simpler model yet. So I
Yeah,
think A's
that's the one I messed up on.
Yeah, I think A
I
is the
jumped right
best
to the
answer.
conclusion. I jumped to the
Yeah.
conclusion.
So yeah, something to look out in these quizzes. You can sometimes have multiple good answers, but you gotta look for the best answer. All right, a couple more here because I gotta wrap up. What's the purpose of folding your data sets? Folds are used for cross-validation, which allow us to have better understanding of how our data is split. So it's not A, nothing to do with polynomials. Not C, nothing to do with calculating R squared. Not D, nothing to do with that either. So it's definitely B here. Last one. This is our residuals, predicted versus actual plots. The blue curve represents the model. The blue dots represent the data. The orange curve represents reality. What's the following is true here? It displays underfitting. That's wrong. Underfitting is where there's patterns that the model is not seeing. This is seeing way too many patterns, right? Notice all the different bimodality of the blue function. So it's underfit. It's not underfit. The model is not a good fit because we are going all over the place with kind of our modality here. We probably just want one smooth function, not all this crazy up and down nonsense. So it's not well fit. There are conclusions that can be made, and that conclusion is that we are overfit. We are identifying patterns that exist in the data that don't actually exist in the data. So we should have overfitting here. 10 out of 10. Give me 100%. Oh, I missed one. Oh
Oh,
my
what did you
God.
mess up?
Oh no.
I
Oh, it
didn't
doesn't
pay
tell
enough.
me.
I didn't pay enough attention to coach you.
Oh, that's the results of the class. Yeah, I'm not sure which one I missed. It doesn't tell me. I
Keep
thought
going
it
down.
tells you which one you miss.
Yeah, we'll tell you 0 out of 1 for that one.
Oh, 1 out of 1, 1 out of 1, 1 out of 1. Oh, there you go. I missed four. Oh, okay. This is a dumb. Maybe it is B. I don't know. This is a dumb
Yeah, it's
question. I
two. It's B. It's B. It says two. That's the order is two.
doesn't it also create like X? I don't know.
But it's a 2-degree polynomial. It's kind of dumb question,
Yeah,
but yeah, it's
I thought it'd be like X and X squared.
pretty trivial or
Yeah,
cat or whatever it is. Yeah,
whatever. So yeah, number four, I think the answer is gonna be B instead of
it's
A. So
B.
it'll be
It's
two
B.
instead of a maximum of two.
It's B.
Whatever.
Yeah.
I'm still happy with my 90. I passed. All right. Just to wrap up a lecture for today, thanks so much for kind of joining. Again, big ideas should be around exploratory data analysis and pandas. So again, for my supplemental law materials, definitely start looking at, oh, they got some more guides now. The exploratory data analysis. I guess it'd be Pandas, Data Viz, Seaborn, stuff like that. There's some really good tutorials out there to learn Seaborn, to learn leaderboards and EDA. So definitely take your time on that. Don't get hung up on all the machine learning content, just because we're going to get back into that in a couple of weeks. Focus more on data wrangling and pre-processing this week. All right, I think that's all I got. Let me check the chat. Otherwise, Hinton, we are ready to let you go. Good job learning regression and good luck with your exam next week. We'll still be here. We'll record it and we'll post it. It's a holiday in the States next Monday, but we'll still record the lecture and put it up. So, good luck with your exam. Hopefully, this was interesting and you learned a little something. And we'll see you in a couple of weeks here. Thanks, Hinton, and thanks everybody for joining and watching wherever you are in the world. Take care and have a great night.
Yeah.